Beyond atmosphere, there's a lot of other characteristics, although none are as in depth discussion as atmospheres are. Another characteristic that we can talk about in terms of planets is whether or not it's tilted. Recall that tilt refers to the difference between the plane of orbit versus where the equator is. If there's no tilt, those two are exactly the same. If there's tilt, then the planet would go below and above the plane of orbit, like Earth. We don't know why all of the planets are tilted or to the extent that they're tilted. However, we have a good guess, just like we talked about with Earth, that impacts are a good guess as to why they have those tilts. The effect of having a tilt is, of course, seasons. Taking a look at which planets are tilted, some, like Mercury, seem to have no tilt at all. There are some that have a lot of tilt. Venus, by looking at this picture down at the bottom, doesn't quite look like it has a lot, but it rotates in the opposite direction as everything else. Everybody rotates counterclockwise. Venus rotates clockwise, and so astronomers hypothesized that Venus was tipped so far over that it's tipped upside down. So it was started off, we think, rotating the same way, and then it got tipped upside down, and so it looks like it's rotating the opposite way. So Venus, although it looks relatively straight up, is tilted quite a bit. Earth, as you know, is tilted 23.5 degrees. Mars has a similar tilt as Earth, 25 degrees. Jupiter has very little tilt. Saturn, you probably recognize that characteristic angle of its rings. Uranus is the really interesting one. Uranus is tilted almost perpendicularly. So as it orbits the sun, it doesn't orbit like this, like everybody else. It actually orbits going up and down. So Uranus has extremely exaggerated seasons because as it rotates, its poles actually point towards the sun, and it almost rolls over as it orbits the sun. Finally, Neptune also has a significant tilt. So really, almost all of them have a good tilt, except for Mercury and Jupiter. Another planetary characteristic that we can talk about are the surface of the planets. The surface of the planet generally refers to what's underneath the atmosphere. One concept we need to discuss is the idea of planetary differentiation. Planetary differentiation refers to the idea that planets tend to be layered. If you recall from your understanding of Earth science in earlier classes, the Earth has a crust, and underneath the crust is a semi-molten mantle. Underneath that is the core, the outer layer of which is liquid, and the center of it is solid. We think that layering occurred because as the planets formed, the densest material would be pulled down to the center, much like if you drop stuff in a pool, the heavier stuff is going, and the denser stuff is going to sink to the bottom, and the less dense stuff will be floating on the top. So iron, being the densest, would have been pulled to the center by gravity first, and then the lighter material, like rock, which doesn't seem light, but compared to iron it is, the lighter material would float on the surface until it cooled. We see that in all of the planets as they form. We see that layering of the interior of the planets. Most of the surfaces of the terrestrial planets are of silica and aluminum because they're the lightest. Another trend that we see as we examine the interiors of planets is the change of pressure and heat. As you go towards the center of the planet, the material is pulled closer and closer together. As that material is pulled closer and closer together, the force of gravity increases the pressure, and just the fact that there's other material so close increases the pressure. That increases the interactions of the particles, making it very, very hot. If you have chemistry, you know that as pressure increases, so does heat, and vice versa. There are other factors that affect what's going on inside of a planet and whether or not it's solid or molten. Tidal forces, for example, we have a moon of Jupiter called Io, and the gravitational pull between Jupiter and the other moons and the other things in the solar system cause such turbulence of pulls inside that it's molten, and so there's a lot of volcanic activity. So it's not the only thing that determines it. When we compare the interior of the planet, once again, we're going to look at inner planets versus outer planets. All of the planets typically have that differentiation we talk about, with the densest material being at the core. In the inner planets, the densest material is the iron. When the solar system formed, remember that the densest material would not have been thrown out as far as the less dense material, which is one of the reasons why we see more hydrogen and helium out in the outer solar system. The iron, being the densest material, would have stayed closer to the sun, making it more common in the inner planets. The mantle then tends to be molten, depending upon which planet we're talking about, and then all of them have the rocky crust that cooled. How much is present depends upon the planet. Mercury is the most iron-rich planet, being the closest to the sun. However, it's cooled completely. The larger size of Venus, Earth, and Mars mean that there's going to be more heat in the center, giving them more of a layered appearance. Less is known about the outer planets. Of course, we've been there less. We have less studies of them. And to get any studies about their interiors means we have to get through their atmospheres, which has also been difficult. But what we're fairly certain, based on their gravity and their densities and so forth, is that they probably have some sort of rocky core. Remember, those heavy metals like iron would not have been flung out as far, so it would be less common as well. We're fairly certain that most of them have rocky cores. Another characteristic about planets we can discuss is whether or not they have a magnetic field. On Earth, we know that magnetic fields can be induced by having a magnetic material moving in a circle. We can make that, we do that in our technology all the time. So, at a planet, the magnetic field would be created in a similar way. A magnetic material such as iron needs to spin, but it needs to flow. We call this the dynamo theory, the idea that magnetic fields of planets result from magnetic materials spinning fast enough to induce the magnetic field. Typically, in order for the metal to be moving fast enough, it needs to be liquid, which then we have to look at the interior of planets and whether or not they have a magnetic liquid material inside to do this. We don't entirely understand magnetic fields. Uranus has a very unusual magnetic field that kind of occurs in pockets, and we don't entirely understand why that is. Certainly the fact that Uranus is orbiting on its side might have an influence on that, but there's a lot that we don't understand yet about magnetic fields. One important characteristic of having a magnetic field is that magnetic fields deflect solar wind, which can be harmful to organic material. And so consequently, one of the dangers of, say, inhabiting Mars or the moon long term would be finding a way to protect the astronauts from the solar wind, because neither the moon nor Mars has a magnetic field. Earth's magnetic field occurs because we have the liquid core. Remember that we have the molten mantle, and then the iron is actually liquefied underneath that, and Earth is spinning fast enough to get that iron moving around to induce our magnetic field. The nice benefit that the Earth has a magnetic field is that the solar wind is kind of deflected by our magnetic field, although at the poles we see some of the particles escaping in. It doesn't cause any danger, but it causes very cool light shows we call the aurora borealis and the aurora australis, or the northern and southern lights. So when we look at which planets have magnetic fields, we see that Mercury has lots of iron, but it spins very slowly. The iron, we're pretty sure, has cooled all the way through, or solidified all the way through, and so consequently, it's slow rotation, and the fact that there's not the iron solid means no magnetic field. Venus has lots of iron, but it's also spinning very slowly, so it's not fast enough to induce a magnetic field. Earth, as I mentioned, yes, we do because of our iron core, iron liquid core. Mars has iron in the core, but it's solid, and so it's not fast enough to have the magnetic field either. They do have little magnetic pockets that we're not entirely understanding either, but not like we have. Jupiter and Saturn, though we don't think they have any iron, their liquid hydrogen is spinning fast enough that it takes on magnetic properties. We call it metallic hydrogen, and so that induces very strong magnetic fields. Uranus and Neptune don't have the magnetic metallic hydrogen, but their ammonia is ionized to induce a magnetic field. Another characteristics of planets we can talk about is the surface of them. So in other words, potentially, hypothetically, if you flew in on a spaceship, providing you could survive the flight, if you flew in on a spaceship, what would you land on? The inner planets, if you recall, have another name called terrestrial planets, which means they have a rocky surface. This comes from the molten mantle cooling or solidifying on the crust. Being that they're rocky means that most of them have evidence of volcanoes, or at least collisions that cracked open the crust while it was cooling, so we can see evidence of volcanic rock there. We see that on Mercury, the moon, and really any of the terrestrial objects. Because of the rocky surface, they also have craters. During the period of the solar system's history, when there was much more debris in the solar system, the same thing that caused the craters on the moon. The planets that have erosion have erased some of those craters, so we don't see as many on Earth. We don't see as many on Mars. Venus, because of its so thick atmosphere, we don't see as much, period. But many of those impacts would have burned up in their atmosphere, much more so than we even see on Earth. So Mercury is rocky. As you can see, it looks very much like the moon for the same reasons that the moon looks the way it does. For much of human history, we didn't have a real great idea of what Mercury looked like. Even the last century, though we've had really good telescopes, we've even sent some probes out there, we didn't have an image of the whole thing. In 2008, we sent the Mercury Messenger probe, which gave us these really nice images of what it looks like. We can see that there were some volcanic activity, but most of the surface is cratered. All of the volcanoes are because we're pretty sure that it's cooled solid through, all of the volcanoes are inactive. Many of the craters filled with lava, suggesting that they occurred when Mercury was still cooling. There's a very large crater called the Caloris Basin. So we think that there was a humongous impact, and it sends ripples on one side all the way through to the other side. We can actually see on both sides of the planet the impact of that impact. And we see these ripples going through around the impact. We can also see scarps. Scarps are basically big cliffs that formed as the crust cooled. I picture it much like you would imagine mud getting really drying out and cracking. When the scarps form, lava didn't seep out to fill in that area, which tells us that the interior is probably solidified. Looking at Venus, Venus is dominated by its volcanoes. So it's a mostly flat area, except it has very active volcanoes. There are 2 continents on Venus that we think, based on our probes that we've sent. And the surface features are controlled by the lava flows. Of course, you know what Earth's surface is like since you live on it. The surface is divided up into pieces that we call plates. Those plates move due to water and wind. We have erosion and weathering, and of course much of our surface is covered with oceans. Mars, you've probably seen a lot of pictures of Mars because in the last 20 years or so, 30 years, we've sent a number of probes and actually landed some probes on the surface. So one of the things you may notice is Mars is called the red planet. That's because it's rusty in color due to the iron oxide on its surface. Iron oxide is just rust. Mars does show evidence of past plate tectonics before the interior cooled. It also shows evidence of hotspot volcanism. Mars has the largest volcano in the solar system called Olympus Mons, and any mountain on Earth, the Mauna Loa volcano in Hawaii, Mount Everest would dwarf compared to Olympus Mons. There's lots of evidence of past erosion and in current erosion, including we see wind erosion. This is a picture actually taken from one of the probes that are on Mars. And we see evidence of water erosion. So though we found evidence of trace water now, Mars once had enough water to create very large basins. Valles Marineris is a canyon larger than the Grand Canyon that would have been caused by water erosion. In talking about the surface and interior of the gas giants, we need to remember that as you get deeper into a planet, there's more gravity, there's more pressure, and there's more temperature. So if we were to try to fly and land on, say, Jupiter, we couldn't. We know this. In the 70s, the probe Galileo was going to crash into one of Jupiter's moons, and scientists thought that was too risky, but they knew that it wouldn't survive crashing into Jupiter, so they sent it into Jupiter, so we know that we can't fly into Jupiter. But imagine we could go magic school bus style and fly into it. You would, looking out the window, it would be like you're flying on a plane through the sky, and then it would be like you're getting into a cloud where it's getting thicker until it's getting really thick, until all of a sudden you notice you're surrounded by water. Remember I talked about one of these spray cans? Inside we have gas. You can see it. It blows gas. But on the inside, I don't know if you can hear that, it's liquid in there. That's because the gas is under pressure. The same thing happens as you get deeper and deeper into Jupiter, Saturn, Uranus, and Neptune. You'd fly through the gas. When you actually landed, would be very difficult to distinguish, and the gas would get more and more pressure until it liquefied. So you essentially would have like an ocean of liquid hydrogen and helium. We're fairly certain, due to gravitational motion and studies about density, that there is a small rocky core. Most hypothesize that they're no bigger than the planet Earth. Jupiter and Saturn, once again, are very similar in their composition. So they have the hydrogen-helium atmosphere gas layer that would eventually become denser and denser and denser until it liquefied. The pressure, as it gets deeper and deeper, would cause the hydrogen to have interactions as well as the spin of the planet, so that the liquid hydrogen would actually take on the characteristics of metals on the periodic table. One of those characteristics I mentioned was being a conductor, which is why they have the magnetic field. At the center, once again, we've got that rocky core, but not likely iron core. Although it's probably got the diameter of Earth, due to the gravitational force, it's likely compressed into smaller area, so it's most likely more massive, but about the same diameter of Earth. Uranus and Neptune, once again, are also very similar. They would have the atmospheric gas layers with the clouds and gaseous hydrogen, and then as the gas got thicker and thicker, it would also have kind of like an ocean of liquid hydrogen and helium. But that ocean would not only be hydrogen and helium, but recall I said that there was a greater percentage of the heavier gases, like ammonia and methane. So that liquid layer would be kind of a mixture of hydrogen, helium, methane, and ammonia, and even some water. And then, once again, it would have a rocky core. We're getting near the end. One of the last characteristics that we'll talk about is why some planets have more moons than others. Recall that a moon is an object that orbits a planet. It's a natural satellite. And most of the moons in the solar system are the result of a planet being large enough to clear its neighborhood. Remember that bigger materials have more gravity, and so a larger object that passes a smaller object, if it's big enough, will cause a smaller object to come near it and possibly orbit it. And so we know that most of the moons are believed to have formed this way. They're asteroid shaped. These tend to be the smaller moons. Even some of the small objects that haven't cleared their neighborhoods have enough gravity to pick up a little something, even though they haven't cleared everything out of their neighborhood. So we see that some asteroids, some dwarf planets, and lots of the planets have captured moons. The bigger it is, the more likely it's going to have more gravity to pull us in. Also, the proximity to the Kuiper belt and the asteroid belt helps with that. And so we see that Jupiter and Neptune have a lot of moons. Saturn does as well. Mars has 2 captured moons from the nearby asteroid belt. Most of those moons, once again, look like this, kind of lumpy, kind of odd-shaped, because the things they're capturing aren't big enough to be nearly round. As we discussed extensively in our unit, not all moons are believed to be captured. Ours isn't. We know that our moon has a collision ejection, or in other words, the impact theory, that something hit it and material cast it outward, formed the moon. We also have theories about co-formation, that some moons formed at the same time. Some moons, we think, are broken up from collisions. So there's a moon called Miranda on Saturn. Miranda looks as if it has been like a broken lamp that has been glued back together, and so our best guess is that there was a collision and the pieces reformed into Miranda. Some collisions form rings, so Saturn's rings likely formed from gravitational pulls that couldn't coalesce back into a moon, so it formed the ring. Jupiter has 4 large rocky moons that likely form this way. And then there's a lot of moons that we just don't really understand how and where they came from. All right, we're in the home stretch. The last thing we're going to talk about are rings. 4 of the planets have rings, and they're the 4 outer planets. The ring material can come from a number of sources. Some of that is trapped dust from volcanoes and debris and meteor ejecta. Some of it is charged particles, and some of it is debris from crashes that gets pulled apart by gravitational forces, and due to the angles of gravitational pull can never be formed back into a moon. So when we look at the rings of the 4 outer planets, Jupiter has 3 very fine, very difficult, dark to see rings. The inner ring is most likely dust. The outer are typically charged particles. Saturn, of course, you know about the ring system. If you ever have the opportunity to view Saturn through a good telescope, do so. It's beautiful. The ring system is most likely formed by moons that have been pulled apart, and due to the gravitational pull of its moons and Saturn create the ring system. There's some thought that if the moon formation had just gone a little bit differently, that Earth might have had rings, which certainly would have been really cool to see. One of the things that makes Saturn really cool is that a lot of the debris is covered in ice, which is why they're so easy to see. Most of what's there is dust particles. There's some bigger rocks, but mostly it's dust. Uranus has 13 rings. They orbit on the equator. Remember that Uranus orbits up and down instead of around, and so its equator actually points upwards. Neptune, like Jupiter, has several dark, thin rings that are difficult to see. However, what's really interesting is that Neptune's largest moon, Triton, is orbiting in a retrograde orbit. In other words, actually literally orbiting backwards. And it doesn't appear to. It literally is orbiting in the opposite direction. And its orbit is getting closer and closer to Neptune. And so it's a possibility that as it gets closer and closer, gravitational forces would actually shear it apart and potentially form a ring system like Saturn. So unlikely that any humans will still be around to see that, because it's in order for it to get closer and closer so far in the future. But it sure would be cool to see. All right, that's it for our discussion of planetary characteristics. We made it. Make sure you see me if you have any questions.